So in this video, I'm going to do another calculating a volume of revolution. So volume of revolution, but in this case, we're going to be using something called the shell method. So last video I made, right, was based on the disk method, but we're going to do the recalculation again. And I'm actually going to give an example of a specific function so we can actually understand the idea, because we can't really generalize it very well because the shell, right, is kind of a little difficult to deal with. So I'm going to first assume that I have a function y equals x squared, my famous y is equal to x squared, like this. And what I'm going to do is I'm going to find the volume generated from x is equal to 0 all the way up to x is equal to, let's say, 10. So I'm going to take this curve and rotate around the x-axis to form a volume of revolution. So this is the rotational axis. So I'm going to take this volume and rotate it. Before, right, we had this, which we take a thin rectangle that's vertical and then rotate it to get a cylinder. And we did that calculation. But we can generalize it very easy because it was a nice function. But the minute we start doing the shell method, we're basically taking a rectangle like this. And you have to be a little careful because this point right here, right, is really the point y, xy. So if I'm rotating this rectangle, right, it creates a shell, a cylindrical shell, and its thickness, right, happens to be dy, and its length, right, in this case, and the reason I chose x equals 10 is actually I would write to, we can't really generalize shells very well, but so you'd have to go to a real curve and try to construct this. So I'm taking y is equal to x squared. So from here to here, right, what is this length? This is actually, this length on one side, right, is actually given by x, or 10 minus x. So it's a little more work to analyze it, so I can't really generalize it very quickly. So this is really 10 minus x is the length of that curve. It traces out, so the distance from here to here is y, and so in this case it happens to be x squared, but I'll use y just temporarily just to get used to it. So basically we're talking about a thin cylinder, and the perimeter of that cylinder, right, that thin shell, right, I'm trying to find the volume of that shell, its dy is going to be 2 pi y, the perimeter, and times the area that's formed, which is times dy times the length, in this case it happens to be 10 minus x. So we can rearrange dy and put it on the other side, but this doesn't really matter. This is called the shell method. So we'll get 2 pi y, which is x squared, so might as well just put x squared in, times 10 minus x, and dx is the volume element. Now I really couldn't generalize it because I really need to know the function, right, where this cylinder, the shell that's created, I have to know the thickness of the shell, which is dy, but the height of the shell depends on how you analyze it. So if somebody gave you a different curve, you're going to have to do some extra work to do this calculation. But basically, I'm going to take x taken from 0 to 10, and so I'm going to be multiplying by an integral operator from, so the integral operator is going to be x is equal to 0 to 10, and so we start integrating. So the volume from 0 to 10 is given by the integral of dv taken from x is equal to 0 to 10, which is equal to the integral of 2 pi x squared. I'm not going to reduce these because this is just setting up the integral. So again, the perimeter of that shell, right, is 2 pi y. And once you have the perimeter, right, I'm taking this rectangle and sweeping a volume. and that volume happens to have a 10 minus sec with the thickness area of dy. And so I'm sweeping it out. And so this is actually the integral setup, right, for y is equal to x squared. I had to specifically do these problems because based on the problem, the shell method, right, is kind of a little more work to do. So for example, if somebody gave you another curve, for example, y is equal to sine of x, and you're going to basically calculate the surface, the volume generated from 0 to pi, then maybe I can create shells from here to here. So the shell, right, you'd have to know is that this curve is y is equal to sine of x. And it's a little more work because the length of this curve, right, you have to take a point from here to here. And that thickness, right, is a little more work to do. So you'd have to calculate the arc sine of y, to calculate the values of x that you need to find this distance. So it's a little more work, and because of that, the shell method you tend to use based on the function that you're working with. But anyway, so this is the general example of volume of revolution using the shell method. So the shell happens to be a little cylinder with a little thickness. That's called the shell.